So I will speak about the subject, and even the abstract was wrong that I sent you, and I will point out what the mistake was. And the mistake was rather essential, as you will see. So just a little bit about the players. So convex body, so first of all, it means it's convex, and it means that body. So convex just simply means that everything is in Rn, so that you have a shape K in Rn, and has the property that for any 2 points, the connecting segment is a subset of K. So algebraically, it means that xy in K, then lambda x plus 1 minus lambda times y is also in K, where lambda is in 0, 1. You know, this is a parametrization of the segment connecting x and y. And the other part, the body, I will mean that K is compact. It may have an empty interior. It's a kind of a shorthand notation for compact convex sets. Another player will be a special type, convex polytope. It means that it's a more discrete object. You have finitely many points, and you take the smallest convex set that they contain. The way I phrased, then it would allow some point in sides, but one can always show that there is a minimal set of points that is needed for the convex hull, and they are the vertices. So for this, I will not use any special properties of polytopes. You just use your imagination. So the cube in any dimension is a polytope, and the simplex is also in any dimension. All Platonic solids are polytopes, and so on. Okay. Now, these are kind of the main players. And also, I give a name for the family. So I write Kn, the family of convex bodies, in Rn. And for polytopes, everything depends on where the vertices are coming from. So, you know, culture is important sometimes, and that you can tell a person's reaction and so on from the way how, from the country that is coming from, say. And in this case, the vertices say, may come from the integer lattice, or might be any any points in the real space. So that if, for us, lambda will be typically either Rn, Qn, so that the n-dimensional vector space of a Q, or Zn. And I will write P lambda, kind of the family of polytopes with vertices in lambda. Okay. Now, so they are the players, and the kind of the functions that we consider. What is a valuation? So we take a abelian group A. A will be any abelian group. And the valuation, I will write Z, it's coming from German, that from Kn into A, or maybe one of the P lambdas into A. It depends. I will always specify. And it has the following property, that if I have two shapes, now I consider the convex body setup. So this is K and M, and I assume that K union M is convex. So it's a special case, so I do not allow this type of situation. and the union is not convex. So in this case, I require that Z K union M, which is now convex, so it makes sense, and plus Z at the intersection would be Z of K plus Z of M. So this condition is important, so otherwise the whole thing doesn't make sense. So there are special cases when it does make, but in general. So this is kind of a, one would say, a very weak property, but it turns out that if it's combined with the group action, and this is the missing part from the essential missing part from the X abstract, then one can have very, very, very strong statements. But before going into that, so let us have some examples. So can you tell me just some examples? So volume, okay. One, it's volume. Z of K is volume. Yeah, surface area. And so it's volume of K, surface area. I will write, say, SK. Now, here already, before continuing, so let us just specify what the surface area is. Just to, for the volume, I think it's clear. It's just the Lebesgue measure. So if I draw a polygon, so maybe the dimension is 2. So what is the surface area? Then just the perimeter. If I write a segment, what is the surface area? I'm sorry? 0? No, actually it's positive. It's n equals 2 in this segment. It's twice the segment. So that in this case, S of K is the perimeter. In this case, S of K twice the length. You know, if you just want to have this notion to be continuous, then if you have kind of a small rectangle around the segment, and kind of the vertical side tends to 0, then the perimeter of the rectangle tends to twice the length. And for a point, what would be the value? Is 0, yeah. And in higher dimension, when the object is kind of n-dimensional, so it has interior, then it's really just the surface, what you would consider a surface. If you have a plate, so an n-1 dimensional object, say when n equals 2, then you have a circular disk somewhere, then it's twice the area. And if it's a lower dimensional, say segment or point, then it is 0. Okay, they were very, very good examples. And yeah, it's also good. Yeah. And I just don't. So probably it doesn't come up. It's a good example, but there is a very trivial example, which is even more trivial than Miklós's example. Yeah, the constant, any constant function is a valuation. And so Z of K is, okay, 1. And maybe the constant 1 is the right one. And now I give 1 a very, very fancy name. I call it Euler characteristic. It's really, but you know, I just want to show off. But I will tell you why I'm doing this a little bit later. Okay, so these things work for actually, these are kind of the typical examples for convex bodies. And naturally, then it's also for lattice polytopes. But say for lattice polytopes, what could be an analog of the volume? So that if maybe P is in, or maybe I use another, Q is in P Zn, then so it's something like this. So what could be an analog of the volume? Say? Of the or the actually the interior points is not good, but all points. Yeah, it's good. So that then Z of Q is just the cardinality. So I write this for cardinality now of Q intersected with Z2. So this is kind of the discrete analog of the volume. Okay, and so probably yeah, these are the most typical ones. Let me add just one more to the original list. And they would go by the name mean projection of, I don't know, dimension, maybe dimension D. It's at most n minus 1. So what you do that you have your original convex body K, and you take any linear subspace of dimension D. Then you can project your body into this linear subspace, and you take the D-dimensional volume of this projection, and you integrate over the Haar measure. So that you consider Haar measure with respect to, so you can take, I don't know, SON, just if you don't want to deal with more complicated groups, the Grassmannians and so on. So that,
I don't understand. What do you integrate again?
So that maybe I take this call to this set to be pi L of K, so the projection into L. And then the mean projection may be capital M D of K is the integral over S1. So we have an n-dimensional, we are in the n-dimensional space. So, so this is the Haar measure on S1. And then what you do, you take the projection into G, I don't know, RD, so that you take the D-dimensional, you fix a D-dimensional subspace, you rotate it in each position, you take the projection, and you take the D-dimensional volume, so that, or D-dimensional Lebesgue measure, so I don't know, lambda D of the projection. So it's maybe if you see it the first time, it's not, so it maybe sound a little bit complicated, but it's not really, and it's a very frequent construction that you kind of consider the average projection or whatever. So just take the expected value of a projection. Now this would be, again, a valuation, because in the D-dimensional space, you do have a valuation, and so one can check that everything works nicely. Now,
so
yeah.
Do I understand correctly that if I take D equals n minus 1, then this is just a constant multiple of the surface?
That's it. Yeah, this is the Cauchy.
Yeah.
theorem. Okay, I was just about to make the same connection, so that actually Sk is some CD multiple of m dimensions and k. So this is the Cauchy integral formula. So it's due to Cauchy. And the value of the constant can be evaluated at the ball, at the unit ball. Probably I do not attempt to write it down because I would get it wrong, but it's definitely, you can do it. So this is one of the very important case of mean projections. The other case is the case d equals 1. So m1 k is the mean width. It's also very important variation. It's not as important as the surface area, but actually it does come up in many situations. So it agrees with the perimeter in the planar case, because in the planar case, n-1 is just 1. What's very nice about the mean width that it is linear in the following sense. And maybe I just write it here, then I exchange so that it. Yeah.
If you take a convex body and then you do this trick, you take a d-dimensional thing, you rotate it around with that, so and you project it, then you get this family of projections.
Yeah.
Can you reconstruct the convex body from those projections?
So the question is that can you reconstruct, say, from the area and so on, so that it's I think in general no, but say in the case of centrally symmetric bodies, yes, the origin symmetric. So that's n for this, but the exact okay. Sometimes it works, and so in general it cannot work because say for the mean widths, then say the unit circle has constant 1 width, and the Rollo triangle also has constant 1 width. But if it is centrally symmetric, then it can be reconstructed from origin symmetric. I'm sorry, or centrally symmetric is also because then you can reconstruct the center as well. So, but I wanted to make a little remark that if I write x plus y, this is kind of Minkowski sum. So so the sum of two sets is the sum of all type of sums that the first vector is coming from the first set and the second vector is coming from the second set. X in capital X and y in capital Y. Then the mean width has the property that m1k plus c is m1k plus m1c. So it is linear in this sense because you can use it for each projection, and the point is that if you have a segment of length 10 and a segment of length 3, then if you add them, then you get a segment of length 13. So for each linear subspace, you have additivity, and when you integrate, then the additivity stays. So it's a very, very nice property of the mean width. So these are the examples, the basic examples. So in this theory about valuations of convex bodies, the basic question is that if you have a valuation with the additional property that you have a group action that say leaves the valuation invariant, then whether you can characterize it. But before doing that, in the big rush, I just forget one thing. So that let me just put back the definition of the valuation. So that it was that z of k union c plus z of k intersect c is zk plus zc, provided that k union c is convex. So one may ask, what happens if I have more sets? So what happens, I don't know, if I have a polygon and I subdivide into, I don't know, in this case 5 sub-polygons, whether I can reconstruct the value of the big polygon from the values at the small polygons, or maybe taking also the intersections and so on. And it turns out that in many cases, so when in all the cases when what I wrote up there, so when lambda is just r to the n, qn, or zn, we have the following property that with this exclusion-inclusion formula still holds, so that we have this exclusion-inclusion, or maybe it's the reverse, so that if we have k1 up to km are convex, and k is their union, then z of k can be written as the sum I equals 1 to m of z of ki minus the sum I less than j z of ki intersected with kj, and plus and so on. So that we have this exclusion inclusion. Naturally, the intersection might be empty. So
is it a problem that, for example, in your picture right there,
yeah.
You might want to do this step by step, like with some sort of induction argument. It might happen that the whole union is convex, but the union of the first three, if you start with
sure.
this, it might happen that
Oh yeah, sure. No, so the inclusion, it only uses intersections.
Yeah, I see that.
Yeah, but you are right. No, if you want to use induction, you need a little trick. What could be the trick? So the problem is what we heard from Lattice. What can you do? So naturally, in many cases like that, first you have to make your life seemingly more complicated. How to make your life seemingly more complicated? So except which way? So maybe I just, so I have this, say, this triangle. So here, if I take just 2, then the union is not convex. So what can we do just to? So basically what you can do that you cut this into using all, say in the case, all lines that occur in the subdivision into smaller pieces. And I don't know, I would say it's full subdivision. So for the subdivision, I mean that you have your original convex body, and then you cut it by hyperplanes. And you consider all the cells that you get. And you want to prove the theorem for that. And then you can use induction, because what you do that you just take one of the hyperplane, it cuts into two families such that both of them have less number of objects. And then you can use induction. And after that, you rebuild the picture. But it was a very good point. So this argument actually works over if the vertices are any real vectors or any rational vectors. This argument doesn't work in the case of integer lattice polytopes, because naturally when I cut, this point might not be an integer point. So actually the case of the exclusion-inclusion formula for lattice polytopes is not very deep, but it's a theorem. So it works, but actually it wasn't known for quite a while. And then it was proved. But for fields it works. For fields it works, but for if you don't have a field, so like the integers, it may not work. So that you can consider subrings, you make that it does not work. So it's not a trivial consequence of the basic defining relation. So for fields, it works because then the intersection point is in the field, so that, or the coordinates of the intersection point are in the field. So, and this exclusion-inclusion principle has a following corollary that if you consider the characteristic function of the convex set, so that if you consider the function, I don't know, I write like this, 1k, it's the function that's, it's the, how to say, so 1k x, no, that's the way. 1k x is 1 if x is in k, and 0 if x is not in k. So this is the characteristic function. Then, but we see that for the defining relation, if I consider the characteristic function of the union and add the characteristic function of the intersection, I get the sum of the two characteristic functions. Actually, for this, I don't even need this convexity thing. And if I have this exclusion-inclusion principle, so that this X inclusion yields that Z extends as a homomorphism from the group generated by these sets 1k, maybe kn, or whichever family into A. So that in this case, valuations are actually group homomorphisms. Now, if I have this family, then I can speak about the value of, say, the union of any two convex sets. I would just express the characteristic function using as a linear combination. So in this case, I can speak about the say the value of this object. And it turns out that the value of this object is the Euler characteristic. So that's why if the valuation is the constant one function. So in this sense, it's really the Euler characteristic. So if you consider it as a group homomorphism, then it's the Euler characteristic. And yeah. So for mean projections, we know what the mean projections are. So maybe just one little technical term. We see that Z is simple if Zk is 0 whenever the interior of K is empty. So the volume is simple, the surface area is not. And kind of the first, actually, when preparing the lectures, I just realized that the first result is around 1830 about evaluations that if Z from actually even P R2 into R or whatever abelian group you want to consider that subset of R is simple and rigid motion invariant, then Zk is just the area. a constant times the area. Naturally, a constant. So the actual statement, it wasn't this. The actual statement due to actually Farkas Bolyai, he's the father of János Bolyai, who is the father of hyperbolic, one of the fathers of hyperbolic geometry. You know, hyperbolic geometry has 3 fathers. So, hyperbolic geometry, yeah. And there were 2 other guys. I really preferred. So I do not want to consider nationalistic. So and he's English and he's German, so that it's really a whole European theorem, and everybody about the same time and independently of each other. But they proved that if I have 2 polygons, so 2 polygons with the same area, polygons, then you can dissect one into the other, so that if I have a triangle and maybe a hexagon, so you can subdivide this into pieces and subdivide this into other pieces. Okay, it's not proper. That so this is the piece 1, maybe pi 1, pi 2, pi 3, pi 4, pi 5, pi 6, and you have I don't know, pi 6, pi 2, and so on, so that you can find congruent pieces into the other one. So there is a bijection between the pieces in a way that the 2 pieces they are congruent. So is it clear? I just don't want to write it down. It takes some time. So here, rigid motion, it means that say SO2 and translation invariant. I'm coming to this. So this was actually, so probably originally it was O2, but it turns out that it works with SO2. So, and actually it's a nice exercise. Kind of, you know that any triangle can be dissected into a rectangle. Just you know, you take the height. Maybe this angle is at least pi half, and then you just make the middle cut and put this piece into here and that piece there. So that if you start with any polygon, you dissect it into triangles. The triangles you dissect into re-dissect into rectangles. So the real problem is working with rectangles. And so now it's, how to say, it's a non-trivial but not too hard exercise that if I have 2 rectangles of the same area, then they are equidissectable. You can find it on the internet, so it's a nice thing. And since we have this, that if I, so it means that if I know the area, then I just take the rectangle with one edge is 1 and the other edge is the area of Q, then the value of the polygon is the same as the value of this rectangle. And now it's easy to see that if I cut it into half, then the 2 pieces have the same volume and so on. Simple. Actually, for this, I need a continuous and rigid motion invariant. So this was kind of the first instance of valuations without knowing the notion of valuation. And then Hilbert asked the same question as Miklós around 1900 in his big lecture. I think it was his 3rd problem. Whether the same property holds in higher dimension than 22 polytopes. Maybe just one remark that naturally from this also follows that if you have any simple, continuous, and rigid motion invariant on convex, planar convex bodies, then it's also constant times the area, because any convex body can be approximated by polygons. So for this we characterize. So that, what about in high dimension? So that Hilbert asked this question in 1900, and by the time the publication of his lectures went into print, the answer was done. Actually, I think the answer was known by the time Hilbert announced the question, and it was a young PhD student then, those days, and he showed that the answer is no. So in 3 dimension, there are 2 polytopes of same volume, equal volume, such that they are not equidissectable. And basically, his argument that I'm not going to present is the first really kind of valuation theoretic thing. So that, what he did, he defined some invariants that are equidissection invariant. And he found 2 polytopes for which this invariant takes different values for these 2 polytopes. So this was the situation around 1900. No, actually, for simple, we will see that simple continuous rigid motion invariant is only the volume. But there is no kind of cheap solution like this, just taking 2 polytopes, equidissect, and so on. So it means that you have to work harder. And you have to work so hard that the actual solution for this problem was due to Hadwiger. I think he proved it around 1955. That he solved this problem, so to find all simple continuous and rigid motion invariant valuation. But actually, he proved more. He didn't even just consider simple ones. So by now, even non-simple ones are characterized. But so the theorem is the following: let Z be, and it's very important on the family of convex bodies, so not on the family of polytopes. Family of convex bodies into R rigid motion invariant invariant. I just want to be sure that I valuation and continuous, yeah. I have almost left out continuous valuation. Then it turns out that Z of k is a linear combination of the mean projections and the volume. They are not on the board anyway, so that it's some, I don't know, lambda d times vk plus some I equal 0 to n, lambda n minus 1 mi, okay, lambda I times mik, where these lambda 0 up to lambda n are real constants. So what it says that basically all rigid motion and continuous rigid motion invariant and continuous variation was listed on the board beforehand. Anything can be cooked up from them. And I think it's, looking at the first sight, it's kind of surprising because it's a very, very small family. And the property is not that strong, what we require. So this is kind of the mother of all characterization theorems in valuation theory, so that everybody tries to get kind of close to this. And now, the first question, actually, which is open since then, it was about 60 years ago. So what about the polytopes? and it's still not down. And let me give you just one indication why. So the known arguments to prove this, actually, so for a very long time there was one argument that was designed by Hadwiger, and about 20 years ago, Dehn came up with a simpler argument, but for each argument there is one kind of essential step that trying to characterize one step that if I shouldn't use z, maybe just I use phi. If phi from Kn into R is linear in the sense that phi of k plus c is phi k plus phi c and continuous, then phi of k is some constant times m1k. You know, I told you that the mean width is linear. And the proof is very simple. So maybe I just present you for n equals 2. So you want to know the phi of a triangle. You just rotate the triangle with small angles so that let us consider for the rotation, maybe let rho alpha be the rotation by alpha, and you consider the average so for some large k, you consider 1 over k times phi of k plus phi of rho 2 pi over k. It's okay, maybe it should be m. 5m plus phi of rho m minus 1 over m times 2 pi k. So what you do that you have the triangle, you rotate a little bit, and then it would be something like that. And then you rotate again and again. So if you take the average and m tends to infinity, then what do you get? What type of shape you get? If you take this, you get a circular disk, because it should be kind of invariant under any rotation. And the only object with this property is the circular disk. So what you get that if I don't know, B is a circular disk with m1 B equals m1 K, then this is just phi of B. And this type of averaging is present in all arguments. And but you get, maybe you start with the polygon, but the average is a circular disk. It's not a polygon. And some of this problem, it couldn't be overcome. So this is a very old open problem.
So you mean that this is already open, right?
This is already open. Yeah. But I mean that for the polytopes, or actually this part that I don't know. So, but the original problem is definitely open. So exactly what the partial solution I don't know. I have to admit that I didn't really have time to prepare from the literature. But if you have any specific question, then I will search it. Okay. So this is one of the known case. For the discrete case, actually the solution is also known, and it's Bethke and Kneser, I think in 1984. Actually, it's simpler, but still a nice proof. maybe I state the best thing is that if Z from on the lattice polytopes into R is SL Zn and lattice translation relation invariant, then Z of, I don't know, Q is some linear combination, some I equals 0 to n, some lambda I, some gi k. And this gi is known. What are they? I will tell you in a minute. Now, this SL and Z, it is just all integer matrix whose determinant is 1. So actually, these are the unimodular transformations. Just so if it is unimodular invariant, then there are n basic valuations that generate. Now, these n basic valuations are related to this number of lattice points. Here, but we have that the number of lattice points in, say, m times q. So that what I do, I have this lattice polytope q. So q is a lattice polytope, and I take all the integer multiples so that I blow it up. I start with a triangle, then I consider twice the triangle, I count the number of lattice points, and so on. And so this turns out to be a polytope. Sum I equals 0 to n, m to the I times gi q. And these coefficients that occur on the left-hand side. This is q. Yeah. Yeah.
For R, so this says that this is an n-dimensional vector space
exactly.
Connected by those elements. And that is an open problem if we just consider polytopes, but do we know anything about, at least about the dimension, not about the generator?
So I don't know. Whether it's finite dimensional. So this is a. I don't know whether it's known that to be finite dimensional. So that's I don't know. It's a good question. So, but for lattice polytopes, naturally it's not rigid motion invariant, but so then it's known. And so maybe just a little bit about these coefficients. That do we have an idea what this what could be Gn of Q? So it should be the main coefficient. If I take a very large integer and blow up.
That's the same thing you already wrote, right? The number of points.
No, the Gn of Q. So, okay, tell me a continuous invariant, not a discrete one. It's the volume, exactly. So if I take a very big convex body, then the number of lattice points, it is just the number of cubes that are inside, the number of basic cubes. So naturally, we have some disturbance around the boundary. But if it is very big, then the boundary is smaller than the whole body. So this is naturally a very Euclidean notion. It does not hold in the hyperbolic space, but in the Euclidean space, we do have this. So that this is just the volume. What would be G0 Q? points. How to calculate the constant term of a polynomial? Yeah, so? One. So it's just one. Now it's actually gn minus 1 of q, it can be expressed. But it's very funny that if n is at least 3, then say g1 of q, kind of the first non-trivial coefficient, it's already a very strange thing. Say when n equals 3, so this is the first interesting case. If you take q to be a tetrahedron that does not contain any lattice point, other than the vertices. So these are the basic objects. Any polytope, lattice polytope can be dissected into this type of objects. Then it really depends on the number theoretic properties of the coefficients. Some Dedekind sums come into the picture. So that by g and q and g0q have geometric meaning, say g1 of q has no geometric meaning. It is number theory. It's really something like that. And maybe just one more sentence for those who know a little bit about algebraic geometry. That so if q is a lattice polytope, then one can assign to it toric variety. For those who, and on toric varieties, the line bundles can be represented by polytopes, and then this the number of lattice points is just the dimension of H0 of this line bundle, of the corresponding line bundle. And what we have here is kind of the Hilbert polynomial. And this is just a very important connection between kind of valuations on lattice polytopes and toric varieties. So it works very nicely both ways. Now, I don't have too much time, so let me just see. So maybe just to give you some more things about more recent research. So actually, what taught this so far, it's kind of the classics. It is the ancient history. More recent one is trying to just relax the assumptions so that, okay, the Hadwiger I relax. So in Hadwiger, we had SON invariance and translation invariance. But what happens if you get rid of translation invariance? Actually, if you have translation invariance, then one knows more. So maybe I don't write it down, maybe just one simple fact that if I want to keep translation invariance, then it's a theorem by McMullen that if Z actually either Kn or P lambda into actually in any group, or maybe for simplicity I just say R, if Z of K is the same as Z of K plus, I don't know, X for X in lambda, whatever is allowed, for any K and X, then there is a polynomial expression like for the lattice point enumerator. So Z of K, Z of M times K is some I equal 0 to N, M to the I times some Zi K, where the Zi Ks are valuations. So what you see that for this, the Hadwiger theorem and the Birkett-Kneser theorems are both kind of subcases of this. Naturally, what the generators are, we don't know. But at least this answers the finite dimensionality when we know. Actually, so this is finite, so that it answers your question. Yeah. I'm sorry. No, it doesn't. I'm sorry, I was wrong. It doesn't answer the finite dimension in the sense that they generate always. It just No, it does. I'm sorry, yeah, because the case m equals 1. It does say that. Yeah. So we have, no, I'm sorry, it doesn't say because zi is, it depends on z. It's not basic. So yeah, I should point out that unlike in the Hadwiger and the Bethke, zi depends on z. Okay. So it's still legit open. I got. So anyway, it's still much easier because then the zik is homogeneous. Zi, I don't know, m times k is m to the I times zik, and then it's much easier to characterize this type of valuation. So that the real question is, what happens if I get rid of the assumption about translations? And Semyon and Lesker proved around 2000 that so he characterized all continuous valuations, continuous and SO n invariant valuations. So it appeared in the annals, but just to see that how difficult the theorem is, that an errata also appeared in the annals in 2007. So that the first version of the proof contained a gap, and then he corrected.
Wait, didn't you say that this was open?
No, he characterized this. So for polytopes. For polytopes, you even allowed translation. So you allow the strongest group that you can think of, and still it's open.
Is this a very rich family?
It's not very rich. It's describer. So the basic idea is that so first you characterize kind of nice valuations that behaves nicely with respect to translation. His first attempt was that considering those that when you fix k and this, you consider this as a function of x, then this is a polynomial in x. And then he characterized those. And this was his representation theory. And kind of the gap was that he assumed that any continuous SON invariant valuation can be approximated by these polynomial ones. So in that case, kind of the idea is that, so maybe I just pointed out that z k plus x would be some polynomial of degree, I don't know, at most 10 or something like this. So, and in 2007 he found a kind of, as somebody pointed out the mistake, and then he realized that he could classify valuations that are more general than continuous polynomial ones, and with those ones you can approximate any continuous ones. So that, but so this one really uses representation theory, because you have a group action, so that this is what you would expect that if you have more. The same thing is not known in the lattice case. So kind of the twin theorem would be the characterization of all z p zn into, I don't know, say R, and SL zn invariant. Or, yeah. Especially with the more general groups. Maybe exactly with R, it might be, no, even with R. So that, or with, also with Rn and so on. So there are other groups that it's interesting. So this is open. So for the other side. And naturally, you can also consider other groups. Say instead of SON, you can, another natural group is SL, Rn. And maybe you don't consider only R valuations, also some other groups that I didn't have time to speak about, and so on. So that this is kind of a recent ongoing research. To some extent, Alaskar's theorem was a real breakthrough because somehow he showed that it's possible to handle the problem. So there is a hope at least. And I think I stop here. Thank you very much.